A robot just ran a half marathon faster than any human ever has. Not close to the world record, faster than it. And that's just one of 4 things that happened in robotics this month that you probably haven't fully processed yet. Here's why this particular moment is different from every other robotics headline you've seen. It's not one breakthrough, it's 4, happening at the same time in 3 different layers of what makes a robot actually work. And when you see how they connect, the picture that forms is something most people aren't ready for. Start with Beijing. At the city's annual half marathon, over 100 humanoid robot teams competed this year, up from around 20 just 12 months ago. Nearly half of those robots navigated the entire 21-kilometer course autonomously. No remote control, no human guiding them through an earpiece. And the top finisher, a robot built by a company called Honor, crossed the line in 50 minutes and 26 seconds. The human half-marathon world record set by Ugandan runner Jacob Kiplimo just weeks earlier is 57 minutes and 31 seconds. Let that settle for a second. A machine just outran the fastest human being on Earth, over 13 miles. And it did it using liquid cooling technology adapted directly from smartphone engineering, the same thermal management that keeps your phone from overheating during a video call is now keeping a running robot's joints from failing mid-race. Now you might be thinking, okay, so robots can run. That's a trick, a party performance. What does it actually mean? The answer is in what running stress tests: structural reliability under sustained load, thermal management across an extended operation window, real-time motion control without a safety net. These aren't party tricks. They're exactly the capabilities that industrial deployment demands. And every robot that finishes a half marathon is demonstrating all 3 simultaneously. But the hardware story goes deeper than any single race. At their 2026 partner conference in Shanghai, a company called Agibot unveiled what might be the most comprehensive robotic ecosystem released by a single company in one event. Their flagship humanoid, the A3, stands about 173 centimeters tall and weighs just 55 kilograms. Built from magnesium, titanium, and TPU, it achieves a power-to-weight ratio of 0.218 kilowatts per kilogram, high enough to run continuously for up to 10 hours with a battery swap that takes 10 seconds. That last detail sounds minor until you picture a warehouse where downtime costs money by the minute. What makes the A3 genuinely different, though, is what it can do in groups. Using ultra-wideband positioning, up to 100 A3 units can synchronize with centimeter-level accuracy in real time. You're not looking at a single robot performing a task. You're looking at a fleet that thinks and moves together. Then there's the hand, and this is where it gets interesting. The OmniHand 3 Ultra T has 22 degrees of freedom in the fingers, plus 3 more in the wrist. It weighs 500 grams, it has a load-to-weight ratio of 10:1, and it includes a palm camera with a response time under 0.3 seconds. The gap between robotic manipulation and human dexterity has been one of the hardest problems in this field for decades. This hardware is designed specifically to close it, and running underneath all of this is a set of 8 AI models that Agibot built to power 3 separate intelligence layers: locomotion, manipulation, and interaction, all tightly integrated. One of those models, called BFM, can learn to imitate a human movement from a single short video demonstration, even in a noisy environment. Another, called GCFM, takes a text description or audio input and converts it in real time into physical motion. So the question is this a product company or a platform company? And the answer, based on what they showed, is clearly both. But here's the layer that most people missed. Researchers at Seoul National University just created a new type of artificial muscle that can physically reshape itself after it's already been built and repair itself if it gets damaged. Traditional actuators, the components that make robots move, are fixed at the point of manufacture. They do one thing. If they fail, you replace them. This new system uses a material called a dielectric elementer actuator, combined with a ferrofluid that transitions between solid and liquid states when exposed to
to heat or a magnetic field.
That means the internal electrode structure can actually split, merge, and reroute itself in 3 dimensions while the device is operating. If part of the electrode is damaged, the surrounding material liquefies and reconnects the circuit. The system heals itself and keeps running. And in testing, after multiple full reuse cycles, it maintained 91% of its original performance. Think about what that changes. Instead of building a new actuator for every new task, you build one that reconfigures. Instead of replacing damaged components, you wait for them to repair. The implications stretch from industrial robots to wearable medical devices, to flexible electronics embedded in clothing. The material science of robotics just changed. And then there's the question of the brain. A startup called Physical Intelligence just released a model called Pi 0.7, and it's starting to look like something the field has been chasing for a long time, a general-purpose robot brain. Every robot today is trained for specific tasks. You gather data for folding laundry. You gather different data for loading a dishwasher, different data for sorting packages. It's expensive, it's slow, and it doesn't scale. Pi 0.7 is trained on a mix of data from multiple different robots, human demonstrations, and autonomous interactions all at once. And it shows early signs of something researchers call compositional generalization. Here's the simplest way to understand that. If you know how to cut vegetables and you know how to use a stove, you can probably figure out how to make soup, even if nobody ever taught you the soup recipe specifically. Pi 0.7 is starting to do the equivalent of that with physical tasks. In testing, it used unfamiliar kitchen appliances it had never trained on. It folded laundry without any specific training data for that exact task, and it transferred those skills across different robot bodies in different environments, which has historically been one of the hardest problems in this entire field. There are real limitations. Complex, multi-step tasks still need detailed guidance. Independent benchmarking doesn't yet exist at scale. This is early, but the direction is now clear. The field is moving away from one model per task toward models that learn once and apply that knowledge broadly. And here's where the whole picture snaps into focus. What happened this month wasn't one breakthrough. It was 3 layers of the same problem all advancing at the same time. The physical layer, robots are now structurally capable of sustained, autonomous operation in demanding real-world conditions. The material layer, the components inside those robots, can now adapt, repair, and reconfigure instead of breaking and being replaced. The intelligence layer, the models controlling those robots, are starting to generalize across tasks and environments instead of being locked into narrow training data. Each one of those alone would be a meaningful update. All 3 moving together in the same quarter is something else entirely. The robots being deployed today aren't the ceiling, they're the floor. And the next version of this story will probably surprise you more than this one did. If you want to understand where that trajectory is going, the next video gets into the specific capabilities that still separate robots from humans, and which ones are closing faster than anyone expected.